we will discuss applications of Fermi-Dirac distribution. To understand Fermi-Dirac distribution, first of all, we need to understand a few definitions. For example, that what is the meaning of Fermi energy? Fermi energy. So what Fermi energy is? The Fermi energy is the highest energy level that electrons occupy in a material at 0 Kelvin. So 0 Kelvin means the absolute temperature. So the expression for the Fermi energy is given by that EF is equal to h bar square divided by 2m times 3 pi square n, and its power is 2 by 3, where this h bar is a reduced Planck's constant. So this is a reduced Planck's constant, and here m is the mass of an electron, and n is the number density. So number of electrons per unit volume. So the second point that we need to understand is the Fermi function, which is actually the most important for our today's discussion. What Fermi function is? Fermi function is given by f of E is equal to 1 divided by E raised to power E energy minus the Fermi energy divided by the thermal energy kT plus 1. What Fermi function tells us? It gives the probability that an energy state E is occupied by an electron at a given temperature in a system of fermions. So this is important, that the system should be the fermionic. So such as the electrons in a solid. So now here we can consider different cases to understand more about this function. For an example, that the energy is too small than the Fermi energy. So in this case, we can understand the probability at the energy below the Fermi level. So in this case, you can see that our Fermi function that will be reduced like this, that 1 over E raised to power, because this energy E is too small, so then that will be actually, you can say, approximately negative infinity, then plus 1. So this is a negative infinity. So 1 over infinity is equal to 0. So this means this will be equal to 1 over 0 plus 1, 1. So it is 1. So this means that the electrons at the energy below the Fermi energy, then the probability of occupying a state is 1. That means that it is 100%. So now what we can consider the second case, that if energy is too large compared to the Fermi energy, then you can see that this Fermi function that will be reduced as the following, that 1 over E raised to power now infinity, because our energy E is infinity, so plus 1. So E raised to power infinity, this is actually denominator is infinity, 1 over infinity is 0. So this means that above the Fermi level, our energy states are empty, so there is no any occupation. So another case you can consider, that for example, that if energy is equal to the Fermi energy, then what would happen? So in this case, our Fermi function will be given by that 1 over, so both of these factors are equal, so then it is a 0 over kT, so E raised to power 0 is 1, so then 1 plus 1, so that is 1 over 2. So then the occupation of the Fermi level, that is half, meaning its probability is half. That means it's a 50% filled. So below the Fermi level, your energy states are completely filled, and above the Fermi level, your energy states are empty. So we can also understand this graphically, that for example, along the y-axis, we have our Fermi function, meaning the probability of finding an electron in a state, and E is the energy. So above the Fermi energy, the probability is 1, and at the above the Fermi energy, it is 0. So this is our Fermi energy at this point. So this is a complete box structure. So Now, what we can do, we can calculate the total number of electrons in a system. So how we can do this, that our objective is calculating the total number of electrons in a system. For this, we can utilize our this formula that we have N, that is the total number of electrons in a system. So this will be equal to the following, that N, which is the total number of electrons in a system, that will be equal to that integration from 0 to infinity times N of E times dE. So let's understand first of all this formula. What Ne is, that is the number of electrons per unit energy interval at energy E. So what Ne is, once again, that it is the number of electrons per unit energy interval at energy E. And here, what we are doing, that we are integrating from 0 to infinity. That means we have considered all possible energy levels. Now, we can write this Ne, that must be equal to G of E times F of E. So here, G of E is the density of states. Density of state means that number of available energy states within the delta E, within the interval of the energy. So now these are the total states, and this function, which is the Fermi function, it is the probability. So now you see, when we will multiply both of them, then we will get our total number of electrons per unit energy interval at any given energy E. Now, if we put this back in our equation, then we can get that the N is equal to 0 to infinity G of E times F of E times dE. Now you see that we are integrating it from 0 to infinity, that we are considering all available energy levels. So we already looked with the definition of the Fermi function that we can actually divide it into two parts, that we are going from 0 to the Fermi level, meaning the Fermi energy. So then we can have this G of E into F of E times dE, plus the second part will be that we are going above the Fermi energy. So Fermi energy to infinity. Then here we will have again G of E times F of E into dE. From the work Fermi function, we know that the probability of finding the electrons above the Fermi energy is 0. Then our this second term will be 0. And here below the Fermi energy, our probability of finding electrons, or you can say this Fermi function, that will be equal to 0. So we will get our result that N is equal to 0 to Fermi energy, then this integral G of E into dE. So this is our very simplified formula, that we can say this is equation number 1. So now we can look at this function G of E, which is the density of states. So density of the states is given by that G of E is equal to 2 times 2 pi times volume times 2 times the mass of electron. Its power is 3 over 2 divided by the cube of the Planck's constant times square root of energy. So this actually, the G of E is proportional to the square root of energy. So here there is a one very important point, and that is this multiplication of the 2. So this 2 is because of the spin quantum number. So we know that the spin of electron is a half, that can be plus and minus. So with spin up and spin down, so 2 electrons could go in a state. So we are multiplying it by 2. So now if we put this back in equation number 1, we will get our total number of electrons as following, that N is equal to 4 pi volume times 2 times the mass of electron, power 3 over 2 divided by the cube of the Planck's constant. So these all are the constants. So then they are not depending on the energy. So then we will apply this integral from 0 to Fermi energy over the square root of E into dE. Now this is a very simple integral. If we solve our this integral, so we can get the following result, that n is equal to 2 by 3 because of the integration of the square root, then times 4 pi volume times 2m power 3 over 2 divided by the h cube. Then here it will be E power 3 over 2 the Fermi energy. So as we are actually doing these all calculations at absolute zero temperature, so we put here 0. So from this formula, what we can do, we can find the relation for the Fermi energy at absolute zero temperature. That will be following. That will be that E power 3 over 2, that the Fermi energy at a zero temperature. So this will be equal to 3 times h cube n, and then divided by, this is 8 pi volume times 2m power 3 over 2. Then this is our formula for the Fermi energy. So remove its power 3 over 2. By removing it, we will get our final formula for the Fermi energy, that is equal to 3n divided by 8 pi n, and its power will be 2 over 3. So Planck's constant has a power 3, so it will left only power 2, then divided by 2m, because we are taking the power on both sides of this equation of 2 over 3. So this our expression is an important expression. So we call it that this is our second expression. And this expression is the expression of the Fermi energy at absolute zero temperature. So this energy, you can understand it in a better way if you compare it with the temperature. So I mean to say that the thermal energy, in fact, so the thermal energy is the Bose-Boltzmann constant times the temperature. So when you want to compare this Fermi energy with the thermal energy, then what we can do, we can say that our Fermi energy, that is equal to the thermal energy. So K is a Boltzmann constant times temperature. So this is for the Fermi energy. So we will call it the Fermi temperature. Now, for example, that we do have this helium gas, so it is the molecular gas. So it has a Fermi energy of the order of 0.94 times 10 raised to power minus 3. So better to write it 9.4 into 10 raised to power minus 4 electron volts. And it corresponds to the Fermi temperature in kelvins, about 10 Kelvin. And if we consider the electrons in the lithium, that has 4.7 electron volts Fermi energy, which corresponds to 54,000 kelvins. And similarly, in case of the electron gas in potassium, its Fermi energy is 2.1, which corresponds approximately 21,000 kelvins. So now you can actually understand the concept of the Fermi energy also in terms of the thermal energy and the Fermi temperature in units of Kelvin. Now we can consider another case, that if our this difference of energy with the Fermi energy, that is too big, meaning that now it is actually going towards the higher temperature. You can say that this is actually our case is that if this energy minus Fermi energy, that factor is greater than the thermal energy kT. So then what would happen to our this Fermi-Dirac distribution function? Our function will be reduced like following, that the Fermi function is equal to 1 over, so the function is e minus EF divided by the thermal energy plus 1. Now we can see that this our numerator is relatively too big compared to the denominator. So then E has too big power. So this factor is too big compared to 1. So we can simply write it that it is 1 over E power E minus EF divided by the KT. Now, this function, we can write it in a more simple form, and that simple form is the following, that our Fermi function f of E is equal to that 1 over E raised to power E over kt minus EF over kt. Let's presume that we have these coefficients alpha, that is negative Fermi energy divided by the kT. What is this one? So you can actually see that it is actually the ratio of the Fermi energy relative to the thermal energy. So this is in fact related with the chemical potential. So related to chemical potential. So you can also write it as you can say the mu, which is the chemical potential, and beta, it is equal to 1 over kT. So what is it? It is simply the inverse of the thermal energy. This is inverse of thermal energy. Okay, so now if we put these two parameters alpha and beta in our Fermi function, then we will get our Fermi function f of E is equal to 1 over E raised to power, so our beta E, then now it will be plus alpha. So we have our the final form of the Fermi function, which is f of E is equal to E power negative alpha plus beta E. So this function is actually, you can say, can be utilized to calculate the molecule's energy distribution in a gas. Then in that case, you can calculate that your particle distribution ns is equal to the gs. So then E power negative alpha plus beta times E. So what is this? This is a general form of Maxwell-Boltzmann distribution. This is a Maxwell-Boltzmann distribution. What Maxwell-Boltzmann distribution tells us, in very simple terms, it says that molecules prefer low energy states. What the heat, which is actually related to the beta, because it is the inverse of the heat, and available slots, which actually corresponds to gs. So that determines that how many particles actually make it to the higher energy levels. So this is a very simple and a general form of Maxwell distribution function. And the main objective of our today's lesson was to understand very simple and few derivations related to the Fermi function and its connection with Maxwell-Boltzmann distribution. Hope you understand it. If you will have any question or any doubt, you can send the questions in the comments section, and we will reply to your each and every comment and the questions. Thank you very much for listening.